Advancing Neurotechnology, Biocompatible Electrodes. For long-term brain interfacing. Introduction. Neurotechnology is a rapidly advancing field that seeks to interface directly with the human brain, enabling applications that range from medical interventions to cognitive enhancements. Central to these developments are electrodes that can record and stimulate brain signals. These electrodes must be both biocompatible and usable over the long term to ensure safety, efficacy, and durability. This report delves into the latest advancements in neurotechnology, focusing on the development of biocompatible, long-term, usable electrodes for brain signal recording and stimulation. The importance of biocompatibility. Biocompatibility is the ability of a material to perform without eliciting any undesirable effects in the host body. In the context of neurotechnology, it is paramount that the materials used in electrodes do not provoke an adverse immune response, cause inflammation, or lead to tissue damage. The brain is a particularly sensitive environment, and any foreign object, such as an electrode, has the potential to disrupt its delicate balance. The challenge lies in the fact that the brain's immune system is highly reactive to foreign materials. This response can lead to the encapsulation of the electrode in a fibrous tissue, which can increase impedance and reduce the effectiveness of the device over time. Moreover, the brain's constant movement, due to processes like respiration and heartbeat, subjects the implanted electrodes to mechanical stress, which can lead to wear and tear or even device failure. Advances in material science. To address these challenges, researchers have turned to advanced materials that offer both biocompatibility and durability. Traditional materials like gold and platinum have been widely used in neurotechnology due to their excellent conductivity and resistance to corrosion. However, these materials are not without their drawbacks. For instance, they can still provoke a mild immune response, and their rigidity can lead to mechanical mismatch with the soft brain tissue, causing damage over time. Recent advances have seen the development of new materials that are more compatible with brain tissue. One such innovation is the use of conductive polymers, which are softer and more flexible than metals, thus reducing the mechanical mismatch with the brain. These polymers can be engineered to have conductive properties, making them suitable for both recording and stimulation. Their flexibility allows them to conform better to the brain's surface, reducing the risk of tissue damage and inflammation. Another promising material is graphene, a single layer of carbon atoms arranged in a two-dimensional lattice. Graphene's exceptional electrical properties make it an ideal candidate for neurotechnology applications. It is also biocompatible and can be functionalized with various molecules to enhance its integration with neural tissue. Graphene electrodes have shown promise in both recording and stimulating neural activity with high fidelity, making them a leading-edge technology in this field. Surface modifications and coatings. Beyond the bulk materials, surface modifications and coatings have emerged as critical strategies to improve the biocompatibility and long-term usability of neural electrodes. Surface coatings can be applied to electrodes to reduce the immune response, promote tissue integration, and enhance electrical performance. For example, hydrogels are being explored as coatings for neural electrodes. These hydrophilic polymers can be engineered to have similar mechanical properties to brain tissue, reducing the mechanical mismatch and the risk of damage. Hydrogels can also be infused with anti-inflammatory drugs or growth factors that promote neural tissue integration, further enhancing biocompatibility. Another approach is the use of bioactive coatings that encourage the formation of a stable interface between the electrode and the brain tissue. These coatings can be designed to release bioactive molecules that reduce inflammation, promote tissue healing, or even attract neural stem cells to the site of implantation. Such strategies not only improve the immediate biocompatibility of the electrode, but also ensure its long-term functionality by maintaining a stable and conductive interface with the brain. Long-term usability and durability. Long-term usability is a critical consideration in the development of neurotechnological implants. These devices need to function reliably over years or even decades, which requires not only biocompatibility but also mechanical and electrical stability. The electrodes must withstand the dynamic environment of the brain, including its constant motion and the presence of various biochemical factors that can degrade materials over time. One of the major challenges in long-term electrode use is the issue of biofouling, where proteins and other biological molecules accumulate on the electrode surface, leading to reduced performance. To address this, researchers are developing anti-fouling coatings that prevent the accumulation of such molecules. These coatings are often designed to be hydrophilic, creating a water-rich layer on the electrode surface that resists the adhesion of proteins and cells. Another approach to enhancing long-term usability is the development of self-healing materials. These materials can repair themselves in response to damage, which is particularly important in the brain, where even minor electrode damage can lead to significant problems. Self-healing polymers and hydrogels are being investigated for their potential to maintain electrode functionality over extended periods. Furthermore, advances in microfabrication techniques are enabling the creation of electrodes with more precise geometries and better integration with brain tissue. For example, flexible microelectrode arrays can be fabricated using techniques like photolithography, allowing for the production of electrodes that conform to the brain's surface and reduce the risk of damage. Innovations in electrode design. The design of the electrodes themselves is also crucial to their biocompatibility and long-term usability. Traditional electrodes are often rigid and bulky, which can cause damage to the brain tissue and provoke an immune response. To address this, researchers are developing new electrode designs that are more flexible, smaller, and better integrated with the brain. One innovative approach is the use of microelectrode arrays (MEAs), which consist of multiple tiny electrodes arranged in a grid pattern. MEAs can record neural activity with high spatial resolution, allowing for more precise mapping of brain signals. These arrays can be made from flexible materials that conform to the brain's surface, reducing the risk of damage and improving long-term usability. Another promising design is the stentrode, a stent-like device that can be implanted into a blood vessel in the brain. The stentrode is less invasive than traditional electrode implants and can record neural activity without the need for direct brain penetration. This reduces the risk of tissue damage and inflammation, making it a safer option for long-term use. Ethical and regulatory considerations. As the field of neurotechnology advances, it is important to consider the ethical and regulatory implications of these developments. The implantation of electrodes into the brain raises significant ethical questions, particularly regarding the potential for long-term effects on cognition and behavior. Additionally, the use of biocompatible materials and coatings must be carefully regulated to ensure they are safe for use in humans. Regulatory bodies like the U.S. Food and Drug Administration (FDA) have established guidelines for the evaluation of biocompatible materials in medical devices. These guidelines require rigorous testing of materials for their chemical, mechanical, and biological properties to ensure they do not pose a risk to patients. As neurotechnology continues to evolve, these regulatory frameworks will need to adapt to address the unique challenges posed by brain implants. Conclusion. The development of biocompatible, long-term, usable electrodes for recording and stimulating brain signals represents a leading edge in neurotechnology. Advances in materials science, surface modifications, and electrode design are driving progress in this field, offering the potential for safer and more effective brain-machine interfaces. However, significant challenges remain, particularly in ensuring the long-term stability and functionality of these devices. As researchers continue to innovate, it will be essential to address the ethical and regulatory considerations associated with these technologies. With careful attention to these issues, the future of neurotechnology holds great promise for improving our understanding of the brain and enhancing human capabilities.